Hey, what's up, guys? This is Chung here. So today, let's take a look at this week's weekly contest problem 1601, maximum number of achievable transfer requests. This is the last problem of this week's weekly contest. I mean, the other three problems are not that good, I know, especially for the third one, the the description of the problem is really confusing. I mean, I spent a lot of time, trying to understand what the problem was. I mean, what is really asking you to do. I mean, I would spend a lot of time on that. I mean, once you figure it out, it's nothing more than a DFS, right? Basically, you just maintain like a hash table with a parent and child, and then in the end, you just do a DFS based on the hash table. Okay, cool. Enough talk about that one. Okay, so let's take a look at the last problem of this week's weekly contest. So we have n buildings number from 0 to n minus 1, and each building has a number of employees. Okay, it's it's transfer season. Some employees wants to move to another building. Okay, and the next one is that you have a few transfer requests here. So the first one means that uh, one person from building 0 wants to transfer to 1, and the other one, this one is this one. One person from building 1 wants to transfer to 0. Same thing, so on and so forth. Okay, and it asks you to return the maximum number of achievable requests. So what does the achievable request means? It means that after all these requests, all the buildings number stays the same. Okay, basically, after the maximum transfer request, the integers, basically the numbers, the integers of each building should stay at 0. Okay. Okay, and for this problem, I spent some time, trying to solve it by some greedy approach, like I will just try to try to calculate all the integrate first, and then in the end, basically I loop through the request, and then I find out the only the degrees the integrate that is does not equal to 0. Okay, and then I just try to calculate the final result based on that. But then I realized that that's not the right approach. The why is that? Because if you do that, right, basically if some of the requests by adding that request will make like two buildings imbalance. Okay, so which means for some request we don't want to use it. But so and then I just abandoned my previously approach. So I start trying. Basically, now the problem comes down to the we just need to try all the combinations. Okay. Then what are all the combinations? So now this one becomes to at each of the requests here, we only have two options. We either use it or we don't use it. And again, so then the problem actually becomes to the what a backtracking problem, right? Basically, at each of the step here, right? You have two options, right? You either use this one or you don't use this one. And we just need to try all the possible combinations, and then in the end we check the which one can give us the so basically by the time we have looped through to the end of this request here, we check if the buildings, right? If the buildings, the integrates, they're all 0, and if that's the case, we'll use the current use the request to update our final answer. Okay, basically that's the basic idea here. So to do that, I'm going to define like an integrate here. Okay, I'm using a default dictionary as an integer here. Okay, and then we have answer. Answer equals to 0. So like I said, I'm going to use a backtracking method here. And the first one is the I here, and second one is the count. So, and then in the end, we call the backtracking method. We start from the first request, and the count is also 0. Okay. In the end, we simply return the answer. So how about the backtracking here, right? Let's try to do the backtracking first. So the backtracking is the first one is that we take i's request, okay, and then the second one is we do not take i's request, okay. So if we take the i's request, so what do we have? We have the integrates here, right? The integrates here, basically, the from and to, okay. We have a from and to. So the from is the request 0, okay, and the to is what? Request 1. So with the integrate, right? So the integrate will be decreased by 1. Okay, and the same thing for the to integrate will be increased by 1. Okay. So now we have a backtracking here, right? So now let's move to the next one, the I plus 1, and then the count will be count plus 1 because we know, okay, we take the current request, which means the count should be increased by 1. So we call it backtrack because after this one here, we're gonna mark it back because the next one is not take this one. And also because everyone is sharing the same integrate dictionary here, that's why for this one after this one we're gonna basically uh, set it back to the original value here. Now the second one is this. The second option is we don't take the current one, okay, which means we have a backtrack just I plus 1, and then the count basically it's empty. We don't change the count because we didn't take the i's request. So what's gonna be the base case? Basically, the base case is if I equal to the length of, okay, let's request length of request, okay. If the I equals to the R here, and what? And now we need to check if all the integrates are 0, okay. I mean we can just use like like the easiest way, right? Or we can actually use if any or anything, but I'll just use this if key in integrate for this. If the integrate, okay, integrate key is not 0, we return. Basically, we just return, okay. Else it means that everything in all the keys in the integrate are 0, which means that this is a valid state. It's a balanced state. We just update the answer with the current count. Okay. Yep. I think that's it. Let's try to run the code here. Unhashable list. Oh, sorry. Here. We need to get the i's request and then the from and to. Oh yeah. Okay. Which one is out of the range? Oh, sorry, we didn't return here. Okay, so cool, submit. All right, cool. So it passed. All right. I mean, uh, I I think this one is like a it is a good problem, you know. It's just that, you know. Okay, sorry. So for the how about the time and space complexity, right? So the time complexity is that at each place we have two options. So basically it's going to be the 2 to the power of r here, right? That's the total backtrack options times what? Times uh do we have a times here? Do we have another uh yeah, and we for each of those okay, so for each of these options here, in the end we will have this one here. So that's gonna be the n here, right? Times n because we will have a for loop here to check everything in all the buildings So to get the final to check to validate the base case. Yeah, so that's the time complexity here. Yeah, and actually there's another way of doing this. Since if you guys scroll down here, right? So I mean, as you guys can see, the request here is only uh the maximum request length is 16, and like I said, each one of the requests only has two options. We either take it or we don't take it. Okay. So then what that reminds you guys is that we can use the mask. Okay. We can use the mask to represent the state of this integrate here. Because right now for the current approach here, basically we're using like this integrate to uh, to help us to track the current state. Sorry, the integrates plus the count to help us track the current state. Okay. And what another thing is we can do is here that we all we need to do is we just use like this like the Bitmask here. Okay. We just need to check basically for anything that's if these requests are marked it's well, I mean it is used, we just mark that request to 1. So still we have a 2 to the power of r total possibilities, right? For all the combinations of the requests. And then in the end, we simply check among all those combinations, okay, what are the valid ones? And if they are the valid ones, can we get the total, what's the total number, the total request for that state? And we just need to get the maximum of that. Similar like this one, but the way we're identifying the state is different. We're not using the integrates and the count. Instead, we only use a single mask here, because with the current mask, we know which request is marked to be used, and from that we can simply reconstruct the integrate here. Okay, and you know what? I would probably I'll try to implement that real quick. So just for those ones for people who is interested in the Bitmask solutions. I'm not a big fan of that, but let's just do it. Okay, so that's that. I'll do it really quick here. So the R is this, the length of the request, okay, and then like I said, in the end, right, we have so we just loop through all the possible solutions of this, all the possible state of this Bitmask. So what are the possible states? It's 1 to the 2 to the power of this length. Okay, that's basically the final state. And mm, and then for each of the state here, right? We have a mask here, right? And then we just need to have like another helper functions here. Helper function has to help us check with the current mask if it's valid or not. And if it is valid, uh, what are the total ones in this mask? So, and I'm going to use the same integrate here. Okay, so default int here. Okay, and then we have a total count of 0. Okay, and then so just say it's just similar here, similar idea here, right? It's in range R here, right? In range for the because we have this number of the bits here, right? So if and we just need to check if this the current bit has like a 1, right? How do we do the check if it is 1? We just do this, right? We do a bit shift to the left by the i's here, and then sorry, okay, by i's here, and then we just do a end with the mask. Okay, if this one is true, it means that uh, the current one is the current bit is 1, and then we just do a count plus 1, and then we do what? We do a from actually I'm just going to copy this one here from and to. Okay, I'm going to copy this one here. Okay, right? Because now we know. Okay, for the ice request, we mark that one to be used. So to use that, it means that the f in degree will be decreased by 1. The 2 degree will be increased by 1. Okay, so and then in the end, same thing here, right? We check this. Once this is done, we simply check if this integrate has everything equals to 0, okay? Because otherwise we simply return 0. Else we return the count. Basically, the count is the number of the request for this mask, okay? And the same thing here, right? The answer equals to what? The max of the answer of this what? The helper of the I here, okay? Return answer. Yeah, I think that should work. Dict, okay. Hmm. Oh, here. Hmm. Okay, run it, submit. Yeah, as you guys can see, this one is pretty slow. Maybe it's because I shouldn't have used the default, and this one maybe I can instead of a dictionary, I can use like a list that will maybe improve the performance a bit. But you guys get the idea here, right? I basically this one is just it's similar like this one, but we're doing like in a reverse way, right? Here we are like taking this state with us. In the end, we simply uh, validate that, right? Validate the final state. And here we are doing the similar thing, but instead we're using a bit mask. So and then we just loop through all the bit mask from 0 to this 1 1 1 1 1. Okay, that's all the possible combinations of the of either use or don't use each one of the requests here. Okay, and with the current mask here, we do the similar thing, right? We first we check we get the the used request, and for each of the used request, we check, we populate this integrate here, and in the end, we check if this integrate is a valid state, and then we just return the count to be so that we can update the final answer here. Cool. Yeah, I think it's a good problem, you know. But for the last one, I was expecting a little bit more. Yeah, maybe some graph problem or a DP problem, you know, something like that. But this one is just nothing else than like I would say it's kind of like brute force way plus a little bit of backtracking. Yeah. Anyway, thank you so much for watching the videos, guys. Stay tuned. See you guys soon. Bye bye.